Edward Obbart. He's with us at the School of Electrical Engineering as well. He's a senior lecturer in nuclear engineering. He teaches on the programs. He's going to tell us about beta photovoltaics.
Yeah, thank you. Thank you, Elias. I'll go again. Yeah, so thank you. I'm a nuclear engineer, and I work at UNSW on nuclear research. My background's in materials, so recently I've been working on thermal properties of uranium silicide for use in accident-tolerant nuclear fuel. And my colleagues also in the nuclear engineering group, represented by the bottom of this slide, work on modelling of nuclear materials, including radiation damage and materials property changes in nuclear structural materials. So I'm in the School of Electrical Engineering, and I guess through hanging out with the space people, I've become interested in space power sources. So historically, space power sources have been based around nuclear thermoelectric generators, radioisotope thermoelectric generators, which work essentially based on the thermocouple principle, which is generating the voltage from just a temperature difference. So these diagrams show you at the right these RTGs used by NASA historically, and that slightly blue one in the middle is the one used in Mars Science Laboratory. So at the center you have this pack of plutonium-238 oxide, which simply gets hot by virtue of being a very strong alpha emitter, and the alpha particles are absorbed by the material releasing heat. And then the heat radiates out onto the cold side, which is space with those cooling fins, and from the temperature difference you can extract a voltage. Now, Plut-238 is quite hard to come by. So it can be manufactured. I mean, all plutonium-238 is manufactured. At the moment it's manufactured from neptunium-237. Neptunium-237 is a byproduct of spent fuel reprocessing. So you can irradiate that with a thermal neutron to get neptunium-238, which beta decays to plutonium-238, and then chemically separate that from the neptunium. As you can imagine, this is challenging and particularly very sensitive technology in terms of its nuclear proliferation implications. And there's few places that actually do it. And I imagine it would also be very hard to procure this material should we want to make a CubeSat that goes far, far away. So what would we do to power a CubeSat in deep space? There are other, of course, radionuclides. There are many radionuclides. And so this is a quick table of some likely power sources. I've put plutonium-238 at the bottom of the table. So you can see there's an energy density column. So the energy density of plutonium-238 is actually not the highest, but it lasts a long time because with an 87 or 88 year half-life, you've only lost a little bit of that energy density after 10 years. That's an alpha emitter. There's also, well, in that table, the others are beta emitters. And of course, that releases energy, quite a lot of energy too. So you still get respectable energy density from the beta emitters. But to extract that energy, you would use what is called a Beta-voltaic cell. The beta particles are emitted with a characteristic energy, and the two plots below there show, on the right, the blue one is the energy spectrum of beta particles from nickel-63, and on the left, the energy spectrum from strontium, yttrium-90. So you would extract them using a beta-voltaic device. Now this is in many ways analogous to a photovoltaic device, but there's some important differences. So photovoltaics work with photons, obviously, but a photon actually has trouble making an electron-hole pair, given its energy. A beta particle decelerating in a device will make hundreds or thousands of electron-hole pairs. And if those electron-hole pairs are created in the depletion region, you can sweep them up and create a current. The problem is that the flux of beta particles is millions of times less than the flux of photons that you get in sunshine. So efficiency is crucial. And also you need to try and make sure that the radiation absorption event, which can I get a laser? Oh yeah, here we go. So there's this is like a diagram showing ion tracks of radiation of beta particles being absorbed in this material. You need to try and match that to the physical scale of the device so that that absorption occurs as much as possible in the depletion region. And then you can extract that current as electron hole pairs. So other important differences is that the shunt resistance needs to be as large as possible because your currents are very small compared to a photovoltaic device. However, the series resistance is not so important because the currents are small and so the voltage drop caused by that current is less. There are some beta-voltaic cells available, or have been available. The one on the top left was used in a pacemaker. The pacemakers were superseded in the end by lithium-ion cells. And there's all kinds of interesting nuclear engineering design problems associated with these beta-voltaic devices, because you can see that pacemaker device, the top left one, actually has some quite significant shielding around it. The reason for the shielding is not for the beta particles, because of course they don't travel far, but for the contamination of the promethium-147 with promethium-146, which is a gamma emitter. So sometimes these combinations are actually unavoidable, so you end up designing around these sort of impurities in your source materials as well. That little chip-looking thing at the bottom is a currently available beta-voltaic cell. It's very, very small power, you can see, nanoamps. But it's been designed such that you don't need a nuclear license to have one, so it can be sold without special licensing. Now I think I've touched on some of the design challenges there about radioisotope separation. Nuclear licensing is important, handling the radioisotopes, and of course designing the device. Here I've just approached these two nuclides I mentioned earlier, the strontium-90 and the nickel-63 beta particles, by calculating using really similar techniques I'd use for calculating radiation shielding effectiveness. So calculating where they deposit their energy in silicon. Okay, if you fire these beta particles from one of these sources into silicon, you can see that the nickel-63, the top right plot, shows you that you're depositing almost all of that energy in the outer 10 microns of a transducer, whereas strontium-yttrium-90, still actually interestingly, even though it's much, much higher power, because the beta particles have higher incidence at low energies, you're still dumping most of the energy into the surface, like the top 10 microns or so, but you have a much longer tail extending into the thickness. So these sort of considerations is what determines your design of a beta-voltaic device. And remember that these are matched to the radiation source as well. So it really is something like an integration of different techniques, from the processing, your sourcing of the radioisotope source, to the characteristics of its beta particles, to the physical design of the device that will capture those beta particles. Which I think sounds like a wonderful engineering problem. Which is also not just a wonderful engineering problem, but one that we should realize that we can quite convincingly tackle here, both at UNSW and in Australia, because we have a research reactor in Australia which can manufacture radioisotopes for applications like this. And as I said, there's this wide open design space of at least 50 pure beta or nearly pure beta emitting radionuclides. So challenges, I think, are in scaling this up, because very, very small current devices exist. But to be able to scale the beta-voltaic effect means that you have to pack a very large surface area into a very small, well, hopefully small device for your CubeSat. And then, given the inherent power density of nuclear processes, you should be able to extract a very useful current. And we are working on this. So, and I'm also here saying hello, and I'm interested in people who might also be working in things like this. So any questions?
Okay, we got time for a question.
How does the I've developed a number of CubeSats and small sats, and the power tray is a complicated one. often you need the size of your battery will be governed by the size of your solar array and your peak power demands. It sounds as if the peak current of these systems will never be that fantastic, but as primary battery, they could be quite useful. What's the reasonable sort of energy density of a system which you project to be capable in the next 5 to 10 years?
Well, these two energy density columns are the fundamental energy density of the energy in your nuclide. So that's about a watt per gram. Yeah, but then you need your efficiency, right? So current efficiency is a few percent. So that's like 100 grams or so per watt, I think you can see from these numbers. So maybe, yeah, 10 milliwatts per gram, something like that.
Okay, we'll have another question.
What radio isotope are you recommending?
At this stage, I'm not recommending one. I mean, historically, okay, there's strontium yttrium-90 is fantastic because it really packs a lot of energy in. That's on that line as well, but it has a problem of, because the betas are high energy, you have to deal with radiation damage in your device. I think if we can approach semiconductor manufacture from increasingly radiation-tolerant materials, I mean, based on energy density, I'd say strontium-90 would be great, but it's got this radiation damage problem.
Okay, our next